Let us now construct relaxation table looking at the operational table. From these equations of residuals, it's clear that at the initial stage when x, y and z all were equated to 0, Rx equals 50, Ry equals 18 and Rz equals 19, which becomes the first row entries of the relaxation table. That is, corresponding to x, y, z all equated to 0, we have the entries 50, 18 and 19 respectively. From among these values of residuals, we will identify the numerically largest residual, or first we will take the absolute values of all the available values of residuals and we will identify the largest among the three. Our intention is to reduce the largest to the smallest, and for this we will make use of operational table. We have 50 is the largest of all the three and we wish to reduce 50 to 0 or nearly to 0 or a very small value. Since the largest of the residual values is located in the Rx column, we have to give increment to x. We have to select value of delta x such that this selected value when multiplied to each entry in the first row, which corresponds to delta x equals 1 in the operational table, will help us to reduce this largest value to a much smaller value. We have when delta x equals 5 and 5 is multiplied to minus 9 as well as it is added to 50, it will give 45 plus 50 which equals 5. Thus, the new value for Rx at delta x equals 5 is 5. This value delta x equals 5 is multiplied to minus 1 and added to 18. That is, we have minus 1 plus 5 plus 18 which gives 13 is the updated value for Ry. We have when delta x equals 5 is multiplied to 2 and then added to 19, we will get 2 into 5 plus 19 equals 29 as the updated value of Rz. From among these updated values of residuals, it's clear that 29 is the numerically largest value. Thus, we have to give increment to variable z. The value of delta z is determined such that this value when multiplied to each entries in the last row corresponding to delta z equals 1 will reduce this largest value to a much smaller value. We have when you select delta z equals 4, 4 when multiplied to minus 1 and added to this previous value of Rx, it will give minus 1 into 4 plus 5 equals 1, which is the updated value of Rx. Similarly, we have when the value of delta z, which is 4, when multiplied to 3 and added to previous value of Ry, we will get new value of Ry, which is Ry equals 3 into 4 plus 13, which is 25. Delta z equals 4 is multiplied along with minus 7 and then added to previous value of Rz, which will give new value of Rz. We have Rz equals minus 7 into 4 plus 29, which is 1. Now we can see that this largest value was reduced to 1. Here we have 25 is the numerically largest value and thus we have to give increment to variable y. The value of delta y is selected such that this numerically largest value will become very small or nearly to 0. If you take delta y equals 5, we have when 5 is multiplied along with 2 and added to the previous value of Rx, we will have 2 into 5 plus 1 which equals 11. That is, we have new updated value of Rx is 11. When you multiply delta y equals 5 along with this value minus 5 and add it to the previous value of Ry, we will have new value of Ry obtained as minus 5 into 5 plus 25 which equals 0. This value of delta y, which is 5, when multiplied to minus 2 and added to previous value of Rz will give Rz equals minus 2 into 5 plus 1 which equals minus 9. In this step, we have 11 as the numerically largest value and hence we have to give increment to variable x. When you give delta x equals 1, we have this delta x value when multiplied to each entry in the first row of operational table and added correspondingly to the previous values of residuals will give Rx equals 1 into minus 9 plus 11 which equals 2, Ry equals minus 1 into 1 plus 0 which equals minus 1, and RZ equals 1 into 2 plus minus 9 which equals minus 7. Here we have minus 7 is the numerically largest value. We take absolute values of all the three values, which is absolute value of 2, absolute value of minus 1 which is 1, absolute value of minus 7 which is 7, and from among these three values 7 is the numerically largest value. Hence we will have to give increment to the variable z. If you give delta z equals minus 1 and multiply delta z equals minus 1 to each entry in the last row of operational table, we will have Rx equals minus 1 into minus 1 plus 2 which equals 3. Ry equals 3 into minus 1 plus minus 1 which equals minus 4. Rz equals minus 7 into minus 1 plus minus 7 which equals 0. Hence we have, when you selected delta x equals 1, this numerically largest value got reduced to 0. Here we have minus 4 is the numerically largest value, and we have to give increment to variable y such that when delta y value is multiplied along with each entry in the second row of operational table and correspondingly added to the previous values of the residuals, will reduce this largest value to 0 or a very small value. If you select delta y equals minus 0.8, we have this value of delta y minus 0.8 when multiplied to 2 and added to the previous value, which is 3, will give us Rx equals minus 0.8 into 2 plus 3 which equals minus 1.6 plus 3 which equals 1.4. Similarly, we have minus 0.8 multiplied to minus 5. Minus 4 will give 0 as the new updated value of Ry. Rz equals minus 0.8 into minus 2 plus 0 which equals 1.6. Here we see that 1.6 is the numerically largest value and we have to give increment to the variable z. In order to reduce this value to the smallest possible, we can take delta z equals 1.6 divided by 7 which will give 0.228 which is approximately equal to 0.23. When you take delta z equals 0.23 and this value when multiplied to each entry in the last row and added to the previous residual values which are obtained from here, we will have new value of Rx is 0.23 into minus 1 plus 1.4 which is 1.17. Ry equals 0.23 into 3 plus 0 which is 0.69. Rz equals 0.23 into minus 7 plus 1.6 which is minus 0.09. Here we have 1.17 is the largest value which has to be reduced to smallest possible value. If you take delta x equals 1.17 divided by 9, we have delta x equals 0.13. When 0.13 is multiplied to every entry in the first row of operational table and added to previous values of residuals, we will have Rx equals 0.13 into minus 9 plus 1.17 which equals approximately 0. Ry equals 0.13 into minus 1 plus 0.69 which equals 0.56. Rz equals 0.13 into 2 plus minus 0.09 which equals 0.17. From here we have 0.56 is the largest value. Thus we have to give increment to the variable y. We have delta y equals 0.56 divided by 5 and which equals 0.112. This value delta y equals 0.112 is multiplied to every entry in the second row of operational table and added to previous value of residuals which are available here. Thus we have Rx equals 0.112 into 2 plus 0 which is 0.224. Ry equals 0.112 into minus 5 plus 0.56 which is 0. Rz equals 0.112 into minus 2 plus 0.17 which is 0.054. Along with the negative sign, we have Rz equals minus 0.054. In this step, we see that almost all the residuals are very much small values and hence we can stop the iteration. When you sum up all the increment values of x, we will have x equals 5 plus 1 plus 0.13 which is 6.13. y equals sum of all delta y values, that is y equals 5 plus minus 0.8 plus 0.112, which is 4.31, and delta z equals 4, which when added to delta z equals minus 1, which when added to delta z equals 0.23 will give z equals 3.23. Notice that when we have decimal values in the relaxation table, here when you have rz equals 1.6, in order to find out the increment value to be given to variable z, we are dividing this largest value using the diagonally dominant z value, which is 7, which will give us delta z equals 0.23. When you divide, you are just considering the absolute value, neglecting the negative sign. Here when you identified 1.17 is the largest and you have to find delta x value, you are dividing 1.17 using diagonally dominant x value, which is 9. Here when you identified 0.56 is the largest and you wish to find out delta y value, you are dividing this largest value 0.56 using the diagonally dominant y value, which is 5. These diagonally dominant residual values may be used to evaluate increment values of variables